We're going to look at some vector addition and resolution, and when we add vectors together we get something that we call the resultant vector. Resolution is taking a single vector and bringing them up into its x and y components. Now I'm going to show you two different methods for doing this. The author of the conceptual physics textbook, Dr. Hewitt, prefers the parallelogram method, whereas the OpenStax textbook, I'm pretty sure, uses the head-to-tail method. I've used both. I don't know that I have a preference for one over the other. Maybe if I'm not using graph paper or ruler, the parallelogram is a little bit easier because it's fairly easy to judge parallel lines. Human eyes are really good at noticing those, whereas head to tail, it's probably better to do it with graph paper or with a ruler to be careful. Now, having said that, a lot of times our diagrams here are just estimates to give us a general idea of where things are going to go, and then we'll do math to get the actual numbers on the edges. And so then when we're doing the math, it doesn't really matter which of these two methods that we're doing. Anyway, you'll notice I had the same pairs of vectors set up here, and I would recommend that you take a moment and copy these down. Certainly if you wanted to just copy the first pair down and pause later on and do that, you can. But I am doing this on graph paper, and I have all of these vectors are 5 by 3s in different directions, and I'm just counting the squares here. This one here I have at a 45-degree angle. You can tell that because I'm going straight through one box, whereas this one here, I forget what the angle is, but I'm going through pairs of boxes here. I believe that makes this a 60-degree angle, but I won't swear to that. But anyway, so take a moment, jot those down, and then let's go. So with the parallelogram method, all we do is we draw parallel lines to the opposite side. So I'm going to draw a parallel line to that one, and a parallel line to this one over here, and then our resultant vector is simply this diagonal here. And in fact, I'm going to change colors here for our resultant. Now, if we wanted to find the length of that resultant, we're going to be using Pythagorean theorem, but we're just going to draw in the resultant that time. For the head-to-tail method, what we do is we pick one arrow, and it doesn't matter which one we pick, but I'm going to pick this one here to be our first arrow, and then we go to the head of it, and we attach to it the second one's tail. And so I'm going to just take this one over here, and then my resultant is simply the diagonal line there. I apologize, this is repetitive. I had to pause the video there to take care of an interruption, but you'll notice on these two, when we have our original vectors at right angles to one another, they give us the exact same result. Now, of course, we're going to get the same answer on these, but the diagrams look super similar. I mean, I suppose head-to-tail method saved us drawing one line, but you'll see how these two methods differ as we move on into our next examples. So for our next one here, again, parallelogram, I'm going to draw a line that is parallel to the other one. And I should point out not only parallel, but also same length. And then draw a line that is parallel to this one. And then there's our resultant vector. Whereas with the head-to-tail method, I'm going to take the 3 here as my head again, and I'm going to move that one to there. And there's our resultant vector. And again, our answers are the same here. It's just a different method of getting there. Lastly here, we have our parallel lines, and then our resultant vector. And with head to tail, moving that over here. 1, 2, 3. And I'll be super honest here, as I actually do these two side by side, I notice how similar they are. I genuinely have been taught that these are two different methods. I've worked with both different methods and they felt different when I'm doing them, but actually drawing them out here, really all the head to tail method is doing is eliminating one line. And I'm finding I'm having to be more careful with my counting as I go down if I'm not using a ruler for this, whereas judging the parallel lines is genuinely easier. Both work, both get us the exact same results. Anyway, I want to show you vector resolution. I'm actually going to use the same three vectors, so I've already knew what those results were going to be when I set this up, and so I went ahead and drew in here pairs of dots, and so I'm just going to take a moment and draw those resolution vectors, resultant vectors, excuse me. What you're going to do is take a moment and transfer these over to here. So sometimes we have two vectors and we want to know what's going to happen when they combine. I don't know, this might be something where you're trying to swim across a river and the river is flowing down this way, or you'll hear airplanes where they're flying and the winds are affecting it. Well, later on in the year, we'll get to where we're not only using this for velocities, we'll use it for forces. And so this might be a sign that's being supported by two lines here. And so then you have two different guide wires supporting a sign, and we're looking at the force vectors there instead, whatever it may be. However, when we have a resolution, you'll notice the only way that we know to resolve a vector is to do it in a boxy fashion. But when it comes to doing these things mathematically, we're always interested in coming up with an x component and a y component. Now, here you'll notice we get the same as what we had over there, but you'll notice there is a drastic difference when we resolve these. So it may be that you're given some awkward scenario like this, where you have these things pulling at funny angles, and really what we're doing is we're taking this 3 here, and I'm going to swap colors again. And the 5 is all in the y direction, and so the 5 is here, but we're getting the y component of the 3. That is, this 3 here is partially in the x and partially in the y. And so what we're doing is we're taking the amount that it's in the y and we're adding that over here. And so you'll notice the x component, this is the x portion of the 3, that's the x portion of the 3 there. And so it may be that you're given awkward angles to begin with, these awkward numbers here. You have to come up with a resultant, and then you resolve that resultant into its individual x and y components. The other way you can do it is like what I did over here, where you can come up with the x and y components of each part and then add those together on your own, and you can kind of go straight from your awkward angles to this. I personally think this way is faster to do it in the two-step method, come up with a resultant, and then resolve that resultant. The other thing I'll point out here too is I drew these such that we always had one down. But let's say you had, and I don't know that I'm going to take the time here to draw these a proper length, but let's say that you have two angles that are not at 90 degrees to one another that are really obscure. Well, what we can do is we can always turn this so that this one's on the x, or we can turn it so that it's on the y. And we can also do that with the other one as well, so that we never have to resolve both of them. We can just choose one to resolve, and the other one we can set all on the y-axis, all on the x-axis, whatever we may want. And so we can kind of define where our xy is by rotating the page here, and that becomes a very important trick, especially when we get the force diagrams, the classic example of which is simply a block on a ramp, and what are the forces on it. We can turn it so that we make the surface of the ramp parallel to the x-axis, or make gravity make the y component of this from gravity be parallel to the y, or whatever it may be, but we can turn it so that we don't have to resolve both vectors. Anyway, finishing this up here then, again, when we are resolving a vector, we're always going to end up with right angles. But that's because, again, mathematically we want to have something in the x and something in the y, and so we're really trying to figure out how much of each of these is in the x direction, how much of each of these is in the y direction, so that we can do our math that way. So those are the two different methods for combining resultants, or excuse me, combining vectors, which we call vector addition, which then gives us a resultant. And these are the two methods, or this is the one method for then doing resolution, which will always give you things in right angles.